Hello friends. So in this session we'll try to understand the concept of the momentum equation. That how we'll find out the momentum equation in a hydrodynamic boundary layer. So for that we let's say we have a flat plate and there is a boundary layer in it. Boundary layer formation in it. There is a boundary layer formation on the flat plate and the velocity profile will be something like this. And this is the upon this is the del u upon del y, that is the velocity gradient. And let's say this is the x direction and this is the y direction, and this is hydrodynamic boundary layer because we are going to find out momentum equation. Fine. And one more thing we have to keep in mind, that here the u velocity is much greater than v velocity. Fine. So let us find out that momentum equation. So we have taken an element here. So what are the forces will apply on that element? Let's see that there is a shear stress which will be this direction, then this is here, that is this direction, and there is a momentum here and momentum here will apply, and there is the body weight of this fluid element. So there are some assumptions. First of all, we'll discuss the assumptions. So first assumption is that we have taken the flow to be steady state 2D and incompressible flow. 2D means what? That u velocity is function of x and y. Also, vertical component of the velocity v is equal to function of x and y. Second, that we have taken the unit depth. We have taken the unit depth perpendicular to the plane of the figure. And what is the third? Third is the fluid properties constant, or we can say constant fluid properties. These are the assumptions. These are very important assumptions. So let us find out the that what are the forces will apply on that. Now let us just keep this fluid element here. There will be some mass of this fluid element, let's say mg, gravity force. Uh, let's say the length and width. The length of this fluid element is dx around x-axis and dy along y-axis. Let's find out the forces. What are the forces applied? So we have taken the force here in this direction because of the shear stress. This is what? This is the viscous force. It will be equal to shear stress into area. So what will be the shear stress? That is mu del u upon del y. And what is the area? Area will be dx into y because we have taken the unit depth. And what about this? In this direction, viscous force will be tau into area, which will be if the shear stress is here, this one. So according to that, we'll apply the Taylor equation. According to Taylor theorem, we can apply mu del u upon del y plus del upon del y del u upon del y into dy into dx into 1. So how we are getting this term? This extra term we are getting because of this elemental depth. Because of this elemental depth, we are getting this term, this extra term. This is we are getting from the Taylor equation, the Taylor principle. Now there will be a pressure force applied on this section. So the pressure force will be pressure into area. And what about the opposite direction? Opposite direction, the pressure force will be with respect to this P plus del p upon del x into dx, because x is increasing here, into dy into y. So these are the forces. So now, according to the Newton's law, the sum of the forces along x is equal to mass into acceleration along x. Okay, or we can say that the net algebraic sum of all the forces acting on the element along x direction is equal to the rate of change of linear momentum of the element along x direction. So, applying the momentum equation or the Newton's second law, will get the resulting momentum equation for the hydrodynamic boundary layer along x direction, which will be uh, something like this: u del u upon del x. When you will balance all the forces, then you will get this equation. That is very easy to find out. V del u upon del y is equal to mu by rho del square u by del y square minus 1 by rho dp upon dx. This is the equation for hydrodynamic boundary layer. So some of the things we have to understand here, that if I talk about this term, so this is the convective acceleration of fluid along x direction. That is convective acceleration of fluid along x direction. So we can also say that this is the Navier-Stokes equation of motion along x direction. Navier-Stokes equation along x direction. I have only written in x direction. You can also find out along y direction. I mean, by equating all those equations. Fine, but no need to find out, because in y direction will not get any important results. There is only one result we'll get. I will tell you after that. So for flow over flat plate, one thing we have to look into that, uh, for flow over flat plate, the pressure gradient dP upon dx is negligible. This thing we have to keep in mind. And if we put mu by rho is equal to mu, that is kinematic viscosity, so the resulting momentum equation for the hydrodynamic boundary layer will be u del u upon del x plus v del u upon del y is equal to mu del square u upon del y square. This is the momentum equation for hydrodynamic boundary layer. And if you put v here, I mean, when you solve this differential equation, so you will get the velocity profile like this: u upon v infinity is equal to 3 by 2 y by delta minus half y by delta cube, which I have written directly in the earlier sessions, that we were getting the velocity profile inside the hydrodynamic boundary layer. It is actually the cubic profile. Fine.